Hello, everybody. My name is Argonsky, and I'm Applications and Technical Marketing Manager for PSG, Power Solutions Group of One Semiconductor. And today's presentation will be power factor improvement methods with their advantages and disadvantages, and the role of power semiconductors in a PFC with a silicon and WBG, wide band gap. PFC, which essentially electrical energy is almost exclusively generated, transmitted, and distributed in the form of alternating current. Therefore, the question of power factor comes immediately into picture. Most loads, 80%, in electrical distribution systems are inductive in nature, and hence have very low power factor, which is highly undesirable. Low power factor causes an increase in reactive current, resulting in additional losses of active power in all elements of power system. It is very important to have power factor as close to unity as possible. Note, please, that leading power factor is also undesirable for power systems. Power factor correction, PFC, in a nutshell. PFC need and why. Power factor is the relationship, which is a ratio of a current and voltage in AC electrical distribution system. Low power factor, electrically speaking, causes heavier current to flow in power distribution lines in order to deliver a given number of kilowatts to an electrical load. Under ideal conditions, current and voltage are in phase and the power factor is 100%. If inductive loads, which is motors, present, power factor less than 100%, typically 80 to 90% can occur. Today's commercial, industrial, retail, and even domestic premises are increasingly populated by electronic devices such as PCs, monitors, servers, photocopiers, which are usually powered by switch mode power supplies, SMPS, and if not properly designed, this can present a nonlinear loads which impose harmonic currents and possibly voltages onto the main power network. The IEC 61000-3-2 classifications and the Class D specification in particular. IEC 61000-3-2 has 4 different harmonic content specifications that's based on the application and power level. These 4 different classes are defined below. Class A, the longest, is balanced 3-phase equipment, which is household appliances, but excluding equipment identifies Class D. Tools, except portable, dimmers for incandescent lamps, but not other lighting equipment, and audio equipment. Anything not otherwise classified. Class B, specific for power tools. Class C, all lighting, except for incandescent lamp dimmers. Class D, single phase, under 600 watts, personal computer, PC monitors, TV receivers, and such. Power factor explained in beer. We prefer Pilsner. As you can see, beer with a foam head would give you a complete pint, shall we say, but the actual beer would only be 60 to 70% of it. The rest is foam. And if you look at, then that's a pretty poor power factor, right? It would have 0.6, where a beer glass filled up with virtually no foam will be better than 0.9. And in this case, the cosine angle between the voltage and current in an AC circuit is known as a power factor. I find it's much easily explained on the beer and the foam head, right? What the power factor involves the relationship between the 2 types of power, working power and the reactive power. And to the right, you can see the difference with the red voltage arrow versus the current and the angle in between. In a perfect world, that red arrow and the blue arrow would be pointing in the same direction with the 0 degrees in between. The power factor correction main perpetrators. Electric motors and displacement power factor problems, that's number 1. Electric motors create powerful magnetic fields which produce a voltage, or what we call a back EMF, electromagnetic force, in opposition to the applied voltage. This causes the supply current to lag the applied voltage. The resulting out-of-phase currents cannot deliver usable power, yet it adds to the facility's required supply capacity and the cost of electricity. Fitting capacitors across motors will reduce the phase lag and improve the power factor. This is a completely separate training that we can cover in the near future. Could work with the passive devices. Main theme of this presentation is the switch mode power supplies, SMPS, and the distortion power factor problems. So whereas the displacement power factor loads do not cause harmonics and their associated problems, distortion power factor loads, such as the switch mode power supplies, will do so unless their power factor is improved. Power factor correction is an international standard. An international standard exists to describe and set acceptable limits for a product's main harmonics generation. Within the EU, that's European Union, Its reference is IEC 61000-3-2, covering equivalent power levels. And we have gone through that already on the 4 classes A, B, C, and D. And again, the class D probably one of the worst, which covers everything else. And it's the battery chargers, computers, you name it. Anything under 1 kilowatt, and in some cases 500 watts. There's 2 types of environment exist: residential, domestic home, and industrial. The state limits and performance criteria. So they tell you what specific numbers the product has to meet. And basic standards for measurement of immunity. The product standard for emissions, which outline the past levels that have to be expected. And it has to be used when no product standard exists as well. So it's called self-awareness. Power factor in active and passive topology. Passive power factor methods: static capacitor, synchronous condenser, and phase advancer. The active power factor methods is boost topology, and this is the main theme of the actual presentation. We have 4, actually it's more than 4, but 4 most popular modes of the power factor: CRM, critical conduction mode; FCCRM, frequency clamped critical conduction mode; CCM, continuous conduction mode; and IPFC, interleaved power factor correction mode. The established and innovative PFC solutions, in this case, passive power factor solutions do exist. The general industry view that as active design, which offers the best power factor improvements. These are typically based on cost-effective boost converter topology and technology. Main reason for using boost in around 95% of all active PFCs is because in this topology, power switches don't directly disconnect themselves from power source, like in a flyback or buck configuration. This causes input current to be continuous. So furthermore, its value can be smoothly controlled from the converter switching components, and making this topologies ideal for active PFC, reducing AC line, noises, and progress. Simplified boost PFC block is below. You can see your inductor and your switch that's going to disconnect, or in this case, shunt most of the voltage top to ground when it's on, and when it's off, the inductor is charging at this point. So this is a very basic topology and the block diagram for that. The PFC boost preconverter explained. The boost topology is the lowest cost PFC for SMPS, where mass production is key to keep overall cost down, but quality up, power factor quality up. Main reason for this low cost is because boost configuration operating in a continuous current mode applies the smallest amount of high frequency current to the input bulk capacitor. In this topology, the value of the inductor at the input is calculated such that it conducts continuously throughout the switching cycle. It is the only topology which allows the noise across the input capacitor to be reduced, which is the major factor that will define reducing the size and the cost of the filter. And the inductive and the capacitive front-end filter is very expensive. And so trying to reduce that, also to increase the power factor correction number, is our goal from this presentation. The PFC boost operation, if we follow the red line with something like that, this is the first stage occurs when the switch 1 on the right is closed, and everything is going down through the basically not necessarily ground, but the floating reference within the bridge rectifier. So in this state, the inductor is being energized by the AC side of the circuit via the rectifier, of course, and the inductor current will be increasing. At the same time, the cage diode PFC, becomes a reverse biased, so that it doesn't conduct. The anode is connected to the ground through S1, and energy is provided to the load by the capacitor. So the next picture shows the second state that occurs when S1 is open. In this state, the inductor de-energizes, the current decreases, and it supplies energy to the load and to recharge the capacitor C. And this picture only shows positive half of the input voltage cycle. The negative half would be identical, except that the current will be flowing through the other 2 diodes in the rectifier. As you can see, the 2 parallel diodes, the other ones would have the 2 other diodes with it. Keep in mind that cycling or switching frequency between the 2 states is done around 100 kilohertz or close to it. Could be above, could be below. With the wide bandgap devices available now, the switching frequency can be even higher, therefore keeping filter components like inductor and capacitor even smaller, and keeping overall size down as well as the cost of the passive components. The control circuit, in order to have near perfect PFC, the power switch components have to be controlled to a very precise degree. 3 major factors have to be sampled and corrected for. The measurement of the output voltage, DC, which has to be constant no matter what the output current is, and that to ensure that it is maintained at the reference level, which is V reference. Measurement of the AC voltage to provide a reference for the inductor current, and the measurement of the average inductor current to ensure that it tracks the rectified AC voltage. The control system would typically be a PI-type loop or PID-type loop control system that ensures that the difference between the reference signals and the required signals is as small as possible. The results of a successful design are improved power factor and the THD, total harmonic distortion, as well as the regulated output voltage. And you can see that the current and the voltage are close to being in phase, and that the current has a general sinusoidal shape with a minimal distortion. If you compare the with PFC, your blue line, versus without PFC, the difference is drastic between them. We're looking for the with PFC, where the current and voltage is in phase. The PFC topologies, where, how, and why. And in this case, we have covered the four top ones. And in this case, we're going to start looking at the continuous conduction mode, CCM. Always hard switching. Inductor value is largest, but it minimizes RMS current. And as you can see, continuous conduction mode means that the current, in this case, as well as the voltage, never reaches zero. So the ripple is low, and it can maintain a very good harmonic distortion, but also can maintain a very low ripple, so the large inductor is not needed. The critical conduction mode, CRM, where you have large RMS current, as you can see, it reaches zero. Switching frequency is not fixed, so it can be varied. And does your device, NCP1606 as an example. The frequency clamped critical conduction mode, which is large RMS currents frequency, will be limited and reduced coil inductance, so the smaller coil can be used for something like that. NCP1605 is a good example of device. The critical conduction mode controllers, for example, which is a borderline conduction mode, and popular for the lighting, LEDs, and other low power applications. It's a very simple controller. Usually can be about 4 pin if necessary, maybe 5 at the most, in a very small package. They're very simple to use as well as inexpensive. And so the CRM consists of starting a new switching cycle when the inductor current has reached zero. As a result, CRM saves the need for fast recovery and no fast recovery diodes to contain internal losses. On the other hand, the switching frequency is by essence variable, and the current ripple is very large. CRM is very popular for lighting and other power applications where they're used to having large inductors. The NCP1660 as an example, a 10-pin CRM PFC controller, which is a state-of-the-art because it has a lot of features in something like this, and it's great for very efficient and compact CRM PFC with the high voltage startup capability on board, so there's no need for extra circuit. And you can do just about anything else in lighting with this device, including the notebook adapters and the high power density AC to DC power supplies. Anything offline appliances that requires power correction, and even the flat TVs that's being used. The frequency clamped CRM, and this is approach introduced by Semiconductor, and it's patented by us, and it limits the switching frequency spread of the CRM circuit. Maximum frequency clamp forces discontinuous conduction mode when the converter operates in a light load and or near the line zero crossing. Without this circuitry, the CRM switching frequency would exceed the upper clamp threshold, and that would naturally increase switching losses. A circuitry is added to compensate the DCM engendered dead time so that the line current keeps being properly shaped. And you can see it on the right. The block diagram is very complicated, but we can go over it in the near future, where you can see the voltage reference versus the average current and the inductor current as well. The good example of such device is the NCP1615, and that's a high voltage PFC controller with an X-cap discharge. And so that works quite well, where you have two options and you can use them both. And it, again, efficiency is increased and the THD is decreased with an improved cost of the controller. The PFC selection process, and this is the components. In order to fully understand PFC and how to select best components for that, we'll go over a real-life circuit for a single-phase input power supply, which is probably the most popular type power supply. Selecting the PFC Boost Control topology, continuous conduction mode. The voltage input is 70 volts to 265 volts, and that's a range because it's a requirement. The voltage output has to be regulated at 400 volts DC. The maximum power is 600 watts, and the switching frequency is 100 kilohertz or above. Power factor achieved has to be better than 0.98, so that's close to 1. And we have to understand improvements when we use the wide bandgap devices such as silicon FETs, silicon diodes. The CCM controller is chosen due to disadvantages. The peak current is lower, and the RMS current factor with a trapezoidal waveform is reduced compared to a triangular waveform, reducing device conduction losses. The turn-off losses are lower due to the switch off at much lower maximum currents, close to zero, right? Or should be. The high-frequency ripple current to be smoothed out by the MI filter is much lower in amplitude, so they do not require a big filter. Lower inductor size, lower capacitance size. CCM controller disadvantages. CCM encounters losses in a MOSFET and can be intensified by the boost rectifier reverse recovery loss due to the reverse recovery charge, which is the QRR. For this reason, the silicon carbide MOSFET in conjunction with the ultra-fast recovery diode or preferred silicon carbide Schottky diodes with extreme low QRR are needed for its CCM mode. The main PFC inductor. Considering advances of magnetic materials, we can look now that is available available on the shelf in what we call swinging choke, where it can work with extreme voltage current swing at minimum maximum loads. I am sorry we don't have an expansion on that, but onsemi does not deal with magnetics, but we do have formulas that can calculate an inductor and point to a few different companies with few different samples that you can ask them for it. The bridge rectifier, something that we have in spades, its use of a higher rated current bridge rectifier can reduce voltage drop, VF, forward voltage drop on a diode, which overall reduces the total power dissipation at small incremental cost. It is also possible to reduce semiconductor losses by using two bridges in parallel. And a good example is one of on semiconductors, our part, DBF 2066, that reduces the VF by half, and therefore your efficiency improves by good 5 to 7%. The MOSFET. In order to select the optimum MOSFET, we must understand that the MOSFET requirements in a CCM boost converter are different. High voltage MOSFETs have several families based on different technologies. For a boost converter, the following are some major MOSFET selection consideration for high efficiency application designs. The low figure of merit, which is the RDS on times gate charge and the RDS on time voltage. Right? The fast turn on-off switching to reduce the device switching losses. The gate plateau, which is the millicapacitance near the middle of a gate drive range to balance turn on-off losses. The output capacitance has to be low, COSS, for low switching energy and to increase light load efficiency. The drain source breakdown voltage, the VBR, or the DSS in this case, to handle spikes and overshoots. The low thermal resistance, R theta JC, is important. The package selection must consider the resulting total thermal resistance from junction to ambient, and the worst case, surge dissipation, which typically under low line cycle that's at 70 volts, pulse skipping and a recovery into the high line while ramping the bulk voltage up. So the worst case scenario is the minimum voltage input, in this case 70 volts AC, maximum output current, in this case 600 watts, right? So the body diode commutation speed and reverse recovery charge are not important, since body diode never conducts. In the CCM boost converter, it's a positive. The FCPF 190 N65 FL1 is an on semiconductor part number, which is a 650 volt super junction 2, a very good cost performance ratio part. And in a case like that, we also have an SJ3, which give you lower RDS on, but it also at the cost of increase in price. PFC component selection process, boost diode, which is always forgotten for some unknown reason. Selection of a boost diode is far from trivial and is a major design decision in a CCM PFC design or any other PFC design. Boost diode is commutated at a high current, and reverse recovery can cause significant power loss, noise, and current spikes. Reverse recovery can be a bottleneck for high switching frequency and high power density power supplies. Additionally, at the low line, the available diode conduction duty cycle is quite low, and the forward current quite high in proportion to the average current. For that reason, the first criteria for selecting a diode in a CCM boost are fast recovery with low reverse recovery charge, followed by forward voltage operating at a high forward current. So, we have quite a portfolio of regular diodes that would actually have fast recovery, low reverse recovery charge, and also VF operating at a high forward current, but enter silicon carbide, SiC, Schottky diode. SiC diodes have capacitive charge, QC, rather than reverse recovery charge, QRR. Their switching loss and recovery time are much lower compared to the silicon ultra-fast diode, and will show in greatly improved performance. Moreover, SiC diodes allow higher switching frequency designs, hence higher power density converters is achieved, as well as the reduction in the footprint and higher efficiency in the process. And currently, SiC Schottky diodes are getting to the point of almost commodity pricing right now. So they're easily available in almost every power level and every package. Another good example of the power factor correction as you start getting up in high power levels is the CCM Interleaved 2 or 3 channel PFC controller. And in a case like this, the reason for it is you can have, instead of one huge inductor, very pricey, you can have 3 smaller inductors with 3 smaller diodes, which will greatly improve efficiency and reduce overall cost, strangely enough. And with the FEN 9672 2-phase or 9673 3-phase controller will give you a pretty good idea of where we can stand. And of course, Semiconductor has quite a variety of the MOSFETs or RGBTs, as well as the fast recovery diodes or silicon carbide diodes for the outputs. The Interleaved PFC, the 2 small PFC stages, and this is the expression why. So P in average over 2 in lieu of a single big one. And in this case, as you can see, even with 2 controllers and 2 switches, still everything is going to be less expensive overall by reducing the size of the inductors and the capacitors, which is still very expensive. And in the cases, if 2 phases are out of phase, the resulting currents exhibit a dramatically reduced ripple, hence the smaller capacitor and smaller inductor. The Interleaved PFC benefits: more components, but 150 watt PFC, for example, is easier to design than a 300 watt one. So you have 2 150 watt PFCs in this case, and just adding them on the output. It's a modular approach, so you can vary your modules at this point. Better heating distribution, extended range for the critical conduction mode, smaller components, which translates to reduced cost, and a smaller footprint, and help meet strict form factor needs. Let's say in the flat panel TVs. Everything is getting smaller now, right? And 2 DCM PFCs look like a CCM PFC converter, and it eases EMI filtering and reduces the output RMS current, which is a win-win situation for any power designer. And thank you very much for your attention. If you have need for more information, please get on to www.onsemi.com. Thank you for listening.